Okay, thank you guys for connecting to this new edition of our seminar here in Modema. Today we have the pleasure of having in the seminar as a speaker, Kostas Papafitsoros. Kostas is a specialist in optimization and imaging processing, and probably most of you remember him from being part of the thesis committee of David. So first, I would like to say again now, face to face, let's say, Kostas, thank you for your collaboration in that process. And today, Kostas is going to speak about learning data-driven priors for image reconstruction. Thank you again for accepting the invitation to be part of the seminar, and the audience is yours, Kostas. Welcome.
Okay, thank you very much for having me. So today I want to talk about a project we started some time ago in Berlin. So it's something I really enjoyed. It was a highly collaborative effort. It started in a hackathon event we organized almost like a year ago. So we just gathered together many people from Berlin, from different institutions, like you see here in the photo. For 2 days, we didn't do anything in 2 days, but we had fun. And the nice thing is, like, after we continue having some discussions, particularly with Andreas Koffler, who should be present here as well. And we initiated that work, and also we invited all of the people that worked in the hackathon event. We have now produced this nice preprint and some conference proceedings that I'm going to talk about today. So just to fix the setup, I think so most of you should be familiar with this. So we are dealing with linear inverse problems in imaging. We have some ground truth we want to approximate, and we have a forward operator A, which is a boundary linear operator, and you can think of it as a degradation operator or some kind of operator that, particularly medical imaging, gives you, it transfers the data to a different space. And of course, you have noise that makes the whole problem ill-posed. Just to point out that for the sake of this talk, I will keep everything in the discrete setting, so there's no function spaces. Okay. And of course, we are all familiar with the variational regularization approach, where you're minimizing energy. You're trying to approximate the ground truth by getting a minimizer of certain energy, which consists of two terms, a data fitting term, a data discrepancy term, which basically ensures that the reconstruction is close to the data in some certain sense, plus some regularization term that makes the problem ill-posed and also imposes some a priori information about the data. And of course, as we know, there's some regularization parameter that I call here lambda, that balances the effect of these two terms. Just to briefly talk about regularization functional, so we have the Tikhonov functional, which uses smooth reconstruction. So this is the square of the L2 norm of the gradient, again balanced with a parameter lambda here. So just a denoising example. So you have smooth edges. You smooth the edges, you smooth the whole image isotropically, you remove the noise, but this is not what you want to do in the end. Then we have, instead of the square of the L2 norm, we have the L1 norm, which is the total variation, where you are able to preserve the edges, but of course you have this staircasing effect. This is a very well studied regularizer. We have a lot of analytical results for these reconstructions. We know how they should look like. And basically everything that it is to be studied for this regularizer has been studied. Just to briefly mention also the TGV, the total generalized variation, which is an inflow convolution type of regularization of first and second order derivatives. I will not focus on TGV on this talk, just I mention it for completeness sake. And of course, in the ModeMat, there's also a lot of specialization in selection of these regularization parameters that I will briefly illustrate here. So, of course, if you choose lambda here to be small enough, so that with a denoising example, you don't regularize a lot, so you have not filtered out the noise, and even though you preserve some details, the noise is still there. And at some point, okay, you play with the scalar lambda here. At some point, you get the optimal lambda with respect to PSNR. And then if you increase that further on, you smooth out the image, so but you also lose some details. And this kind of tells you the need for some kind of spatially varying regularization parameter that you want to have. So you want to have high regularization here in the background in the homogeneous areas, and small regularization in the detailed areas. So this can be preserved better. And then go from the scalar total variation regularization to the spatially varying, where basically the lambda now comes inside the L1 norm and is now a function. And the discrete setting will be like a large diagonal matrix with different values on different ends in the diagonal. So different weight at different, you have a different weight at the different pixel or voxel, depending on your application. And this is a non-exhaustive like a literature review on spatially varying total variation. Things started it back in the day, in the early days with Strong and Chan. Then Dong and Hintermuller produced some papers. It was also studied analytically by Zalal Zai, and we also did some work here with Carlos Rautenberg and Michael Hintermuller, 2017. In the context of parameter selection, that was also a specialty of the group of Juan Carlos in collaboration with people from Cambridge, Caroline Sonlib, Luca Calatroni, Tomo Valkonen. They studied all these things. Of course, we also saw the PhD thesis of David, who also studied this problem more analytically. And I just have to mention that when it comes to spatially varying total variation, and in particular for parameter selection, what we have seen mostly is for denoising and for static 2D inverse problems. There's some exceptions here. So Yiku Dong and Carola did some work on tomography. And I think Monica Pagiola and Luca Calatroni also work on some super resolution problems. But again, it's in 2D, so there's no like dynamic inverse problems that you will see this spatially varying total variation. And again, something about the expertise of this group is how to select these parameters. So bilevel optimization was one prominent method that started back in 1 decade ago. So you set up a bilevel problem where you want to minimize an upper level objective. This is just, for instance, it will be just a square difference from the ground truth. So X now is a minimizer of the TV or TGV or whatever regularizing problem you want to think of. And it's the solution X now depends on the parameter, the regularization parameter lambda or capital lambda. So the small lambda here will denote the scalar parameter, and the capitalized lambda will always denote the spatially varying parameter or spatio-temporally varying parameter, as we'll see later. So what we're trying to do here is trying to maximize the PSNR. So this has been studied a lot. And this has been also called supervised learning. So it's a supervised learning approach. You're using the ground truth to estimate the best parameter. I remember a talk by Luca Calatroni where he also used the term shallow learning, because you don't have like any deep neural network, but you have like a parameter or basically a function that you want to estimate, but there's no any layer structure that you are taking advantage of. And there's also this unsupervised learning that we worked a lot recently in Berlin, where you now consider a different upper level objective that does not involve the ground truth. And you can estimate such a parameter, again, scalar or spatially varying problem for without using the ground truth. And just an example that it makes sense, because here for scalar lambda, the lambda, you can see that the lambda that minimizes this upper level objective is basically close to the one that maximizes the PSNR. So this is another way to estimate this parameter. And just a simple example. So just a denoising example. This is how the scalar TV reconstruction will look like, and this is how the spatially variant would look like for the unsupervised learning of this spatially variant parameter here. And you see, for example, the weight drops in the eyes here of the animal, where you have a lot of details. So basically, you don't regularize a lot in this eyes area. Okay, this is about bilevel optimization. And of course, in the recent years, we've seen like a boom of deep learning based methods that are used in imaging. It's hard to keep track on all the developments that we see every day almost. I just have here in the box the supervised learning setting. So and theta, calligraphic N will be a neural network. Theta will be its parameters, its weights and biases. And basically here you're trying to minimize this quantity. I guess it's a loss function over these neural network parameters. You can also have regularization on the weights. So you're trying to learn some weights. So the output, given some data Z, the output of your network will be close to the corresponding ground truth of this data. So here you supervise the setting because you use the ground truth and pairs of ground truth and corrupted data. Okay, so we have also many reviews here. Of course, if you do imaging like that, let's say in the direct supervised learning setting, you might observe quite instabilities in the process, in the results. You might see the creation of artifacts, as was pointed out in that paper here. So what people are trying to do during the last year is to combine these model-based methods, these variational regularization methods, with these deep learning approaches to take to take the best of both worlds. On the one hand, you want to keep this interpretability of model-based methods. You want your solution to have certain properties that are inherited from this model-based regularizer. And on the other hand, those deep learning methods have produced state-of-the-art, and they are very flexible, very adapted to the data, and you want to keep that element here. And again, there is a plethora of literature of how to do that. There are many different ways people have been combining deep learning and model-based methods. And this is, again, by no means an exhaustive list. I just have some examples here. Even when it comes to the reviews, it's hard to keep on track because there are like reviews coming out very often. So how can you combine these things? So one way would be to learn a regularization functional from data, R, and then use that as a functional in a variational scheme, data fitting plus regularization scheme. So this, for instance, we have the adversarial regularizers by Lund, Sockter, and Carola. Some work by Markus Haltmeier, and again, this is by no means an exhaustive list. Another way to do that, you want to maybe you don't want your reconstruction to be exactly the output of the network, but you want to be close to the output of the network. In particular, in the first paper, the authors tried to they have a generative network, and they were trying to impose the reconstruction to be close to a generative network. And Andreas Koffler with co-authors, they also had like another iterative approach that was doing something similar. Then we have these plug and play regularizers, where basically you substitute the proximal operator in some iterative scheme. So the proximal operator resembles a denoising, some L2 denoising plus a regularizer. So for TV will be L2 TV denoising, and you often encounter that in iterative schemes, and then you substitute that by some learned neural network based denoiser. And this is It's the so-called plug-and-play method. And another approach, the last one I have here, is some you have some iterative schemes. Let's say the primal dual hybrid method by Jean-Paul, hybrid gradient method by Jean-Paul, and then you try to learn to take some components of that iterative scheme and substitute them by neural networks by preserving some essential elements, for instance, the communication or the correspondence between primary and dual variables. So you keep some elements of this learned iterative scheme, and the rest of it you substitute it by some neural networks, some highly expressive neural networks, and then this turned out to work really well. I just included 4 reviews here. So the first one is the DACTA numerical review by Simon Arids and co-authors. The second one is a review on learned schemes, on unrolling schemes that we're going to focus on today. The third one came out recently, is again a survey on this combination of deep learning and model-based methods, focusing on converges guarantees. And the fourth one, also out recently, is a review on plug-and-play methods. Okay, so now let's go back to our parameter learning. People have been trying to use neural net to combine neural network approaches with the parameter learning. For instance, I think the first approach was this first paper, and there's also a short note by Luca Calatroni and some co-authors. So this is kind of, let's say, learn the regularization parameters through neural networks in a supervised learning setting. So let's say you have, again, pairs of ground truth and corrupted data, Zi and Xi true. And given some pairs, let's say you can employ a bilevel scheme, as we saw before, to compute the optimal lambda I. Okay, so for this Zi, because you have the ground truth, let's say you can employ a bilevel scheme that we all know, and you can compute the optimal lambda I. But now you have created this new set of pairs, which is now which consists, so you forget the ground truth, and now you have the corrupted data and the optimal lambda I. So now you're trying to learn the map from the data to the lambda I, to the regularization parameter, and you do that through a supervised learning setting. Okay, so again, you take a network, your favorite, let's say CNN, convolutional neural network, which is highly expressive, and you want the input of the network to be the data, and the output will be some regularization parameters, and you train it, so it does exactly that. So this is the offline phase, and then once you have trained the network, and let's say you have obtained some new data, then you can just apply the network to the new data, you get a parameter, and then you solve your variational problem. So this is like an offline phase and online phase. So this has been done in that paper. In the second paper, it was done for denoising. The first paper for denoising for Scala parameter again, and some tomography problem. Of course, one problem here is like if you have large problems, let's say 3D, space and time, so in dynamic, producing these optimal lambda I's, especially if you want them to be spatio-temporally varying, can be computationally intensive. And you have to do that every time you have a new task. So you have to do this offline phase every time you have a new task. So it's not easily generalizable. So we started from that, and we introduced this new method, which I call here a deep unrolled scheme. So again, I write down the inverse problem, and for the sake of this work, we focus on TV. So we have a weighted TV problem. And now we construct a network that will estimate this lambda, this spatially or spatio-temporally varying lambda, without using any ground truths as it was done here. So we skipped completely this offline phase here. And we did that through algorithmic unrolling. So let's say the first step will be to choose a highly expressive over-parameterized convolutional neural network with some parameters. Here we choose the UNet. And we also, the second ingredient is an iterative scheme that solves this problem. So here we just chose the sample-epoch method, the primal dual hybrid gradient. So ST now is an iterative method such that when t goes to infinity, x sub t, the iterates of the method, so the primal iterates of the method, converges to a solution of the variational problem. So we go and we unroll that. So we just fix a t where we'll stop this iteration. Of course, this iteration now depends on the parameter, but before that, we essentially concatenate this CNN, this net sub theta, which has input some initial approximation of the data. So x0, say it's some, let's say, naive approximation of the data. In MRI will be, so of the ground truth. In MRI will be, for instance, the zero field solution, and then you take the inverse of the Fourier transform and you produce x0. So give us some x0, this passes through the network and produces some lambda theta, and then this lambda theta is passed to the unrolled scheme, and the output of the network is xt. So if now we compose this function, these functions, we have our final network, which is now a concatenation of two different things, the CNN and the unrolled scheme. The input will be x0, some approximation of the ground truth, and the output would be the t iterate of the sample-epoch method with which lambda, the lambda that has been computed through the network. So I just have it here written as well. So again, it's the composition of the t iterate of the algorithmic scheme with the output of the network that we have here. So this is now a function, let's say fixing some so x0 you can see it as a function of z, and now the whole thing will be a function of z. Okay, here I have it as a function of x0. So and now you can train end to end. So now let's say you have again a set of training pairs, so the supervised learning setting. So you have some ground truth and you have some data, and this is again a way to produce this initialization x0. So you assume that the data has been produced in the usual way. And now you train the network end to end. So you want, for instance, the output of the network to be close to the ground truth in the sense of some loss function. So you see there is no direct involvement of some ground truth optimal regularization parameters. This is done somehow in between. So these lambda theta are computed in an indirect way. So if you train this network, you want the output to be close to the ground truth, and indirectly you want your lambda theta to be chosen in such a way such that when you plug in this lambda theta to this unrolled scheme and you run it t times, the output would be close to the ground truth. And you can also consider some regularization for the weights. So this is another illustration of what I just said. So you have an input, let's say you can think of it as the data. So this is just a naive reconstruction. This will go through the network, through this convolutional neural network, and it will produce some maps. And these maps now will be fed into some unrolled algorithmic scheme that solve your initial problem. And here, as I said, we focus on the TV problem, and the algorithm we choose is the primal dual method. And then after t iterations, using this lambda that was produced by the CNN, you get an output. And then you want to force this output to be close to the ground truth that you have. And because we also want to focus on dynamic inverse problems, we consider here the simple version of spatiotemporal TV. So x now is a function of two variables. So this bold x is a function of space, xy, and t, and time. So we have now this expression of spatiotemporal TV. And each component is weighted by a different weight. We have this lambda xy for the first spatial component, and the same for the second spatial component, but a different one, lambda t, for the temporal component. So we weight the spatial and the temporal components differently. And all the components, all the capital lambdas, so lambda, capital lambda xy, and the capital lambda t, are a function of both space and time. So we have now this spatiotemporal varying parameters, which we're going to see how they look like in the numerics. And as I said here, we use this highly expressive unit that is able to over-parameterize this regularization parameter. So in a sense, before in the bilevel scheme, let's say for a scalar parameter, you have only one quantity, but here you have really an over-parameterization of the regularization parameter, and this over-parameterization is done by this TNN. So we also did some consistency analysis because we want to check that everything is as it should be. So the first box is again the supervised learning we are doing. So we have this n theta t. So this is our network, which again is a composition of this CNN and the steps of this of the primal dual method. And we plug this in a loss function. We do the supervised learning. But let's say you are not restricting yourself to t, but you're really taking the solution map of this algorithmic scheme. So now here S star is really the solution of the variational problem with data z and regularization parameter capital lambda theta. And here we want to see the relationship between the minimizers of the first problem as t goes to infinity and the minimizers of the second problem. Of course, again, that was mostly like a sanity check, because when you do the supervised learning training here, you want your network to generalize well. So you really, first of all, you cannot produce global minimizers because the problem is highly non-convex, but maybe also you are not interested in computing the global minimizers because you want some generalization to happen. So basically you stop your iterations according to some validation set. So essentially you do some early stopping. So you are not even computing stationary points here. But nevertheless, we're going to check that this consistency as t goes to infinity holds for the global minimizers. So and we did that, and we did that for this specific algorithmic scheme we're considering, the PDHG symbol POC, which I wrote it here just to have this notation. So we have as we know, the symbol POC scheme is used to solve the problems of this kind. And here I have these expressions for f and g for the particular weighted spatially varying TV problem. And here, for instance, the x, so x and y are the dual primal variables, and you have this extrapolation step. So you have also this in the proximal operators, you have this step sigma tau, and then you have this extrapolation variable theta. We had some assumptions for this consistency analysis. First of all, we wanted the operator A to be injective, and this might seem restrictive at the first glance, but all the numerical examples we considered, even in the MRI one, that was the case. because of this sensitivity called sensitivity maps in MRI. For the fidelity term, we also want to be strongly convex and Lipschitz continuously differentiable, and that implies that also the solution map is well defined, is a single value. So we had all the ingredients such that our variational problem has a unique solution. And then for the parameters, sigma and tau and the subgroup POC, we want them to be small enough such that this matrix here is symmetric positive definite. That means it defines a norm. And then because we wanted consistency of minimizers, and this calls for gamma convergence arguments, we also wanted the appropriate conditions on the objective functions. So this function R for the weights here, we want it to be lower semi-continuous, and we also want continuity of the objective. So the loss function has to be continuous, and the network itself, the CNN, has to be continuous, and the regularity of the network is controlled by the regularity of the activation function. So, and this is of course something usual for CNN. So the activation functions are typically continuous. So we have these statements. So the first one, you can also see it in David's thesis. This is something that is also proved there. And we also cite it as the way we prove it is by citing the paper. So the solution map is Lipschitz for every z. And okay, you have this bound here on the Lipschitz constant. So lambda min is the smallest eigenvalue of this matrix here. But that was not enough. So we also want the solution map to the T iterate to be Lipschitz, and that was not immediately obvious, even though the solution map is Lipschitz. The unrolled, let's say, solution map, it's also Lipschitz, but you need to work out a bit the proof. And if for bounded lambdas, or for uniformly bounded lambdas, we also have this sublinear rate for the iterates. So of course you have convergence of the iterates, the solution, and we also have this rate t to 1/4. And the last one is like when lambda t converges to lambda, you have this kind of diagonal property. As t goes to infinity, you take the tth iterate that corresponds to the lambda t, and if you send it to infinity, then this goes to the corresponding limit. Just to point out that this is just an ingredient for the proof of the statement that is going to follow. In our unrolled scheme, the lambda is computed by the network, and then it stays fixed. So we don't have any lambda t go to lambda. This is just a technicality for the proof. And then basically the last point is the one that tells you have gamma convergence. So let's say you fix the training set, and you have these loss functions that, if you don't remember, these are the ones. So these are the ones we have in our scheme. And this is the limiting one that results from when you don't consider a stopping t, but you just take the solution map of your algorithm. So yeah, so these two objectives, so lambda t gamma converges to lambda star as t goes to infinity. And from the moment you have gamma convergence, you have the corresponding statement for epsilon minimizers. So if you have that theta, if you have the theta t is an epsilon minimizer of lambda t, which is defined like this. Then if theta t or converges to theta in the sense of a subsequence, then the theta will be exactly a minimizer of the original problem. So this is the consistency result. Just to point out that here the statement does not need, you don't need to prove that the lambda star has minimizers. In particular, if you go here, let's say in the second box, and you're wondering if this problem has a solution, which I implicitly declare this by writing this min, it's not so obvious if you don't have some coercivity. So of course you need some coercivity on theta, which you can probably get if you use the ReLU function, but if you don't, and if the coercivity is not imposed by these regularizations through some, let's say, box constraint set, then it's not so obvious that you have coercivity with respect to theta, but nevertheless, this last theorem here does not need this statement. So this is a statement that if you have accumulation points on the epsilon minimizers, then these accumulation points are minimizers of the original of the limiting problem. And again, this is a statement for minimizers, which is probably a bit far away to the to what we did. And I'm gonna show now some numerical examples. So again, so the usual series of images. So you have some ground truth here. So this is a dynamic MRI. This is the specialty of Andreas Koffler. This is the ground truth. This is, let's say, the initialization, this X0 I was talking about, the zero field solution. This is the best color with respect to PSNR, and this is now the output of the here spatially varying TV. So you see you have like better details. And you can see some quantitative plots, and in general, this spatially varying parameter that is produced by the network is the one that makes sense. It makes sense visually, and it makes sense with respect to SSIM and PSNR quality measures. So you consistently have improvement. And now the cool thing is, like Andreas did these experiments also for dynamic problems. So maybe here I can. Okay, so here when you see these are the lambda xy. So these are the spatial temporal parameters that weight the spatial component of TV, and lambda t is the spatial temporal varying parameter that weights the temporal component of TV. And if you see here yellow values, it means that it's high values. If you see purple and black values, it has low values. And now these are these really cool animations. For instance, you see here how the ground truth looks like and how the zero field reconstruction looks like. And these are the corresponding parameters that are spatial temporally varying. So this, the one on the left, weights the spatial component of TV. So gradients with respect to X and Y, and the one here in the middle weights the gradients with respect to time. And this is the corresponding reconstruction. And the nice thing here is that in the area where you have a lot of movement, so this is the heart, for instance, moving, the parameter that weights the temporal component of TV, in that area it's small. And that makes sense because you have a lot of movement. You don't want to regularize a lot there. You want to regularize a little bit. Whereas if you don't have a lot of movement, it makes sense to regularize across time, because basically, essentially, you will average across time there. So in some sense, this spatiotemporal varying parameter decouples through this temporal component, decouples the spatial and the temporal component of the TV functional. And okay, we're a big group and we did a lot of numerics. We also had some numerics in quantitative MRI that I did not include here in the interest of time. So this is an application in tomography. So now our forward operator is a Radron transform. That will be the ground truth. This is the filtered back projection. This is our corresponding X0. Now this is the best reconstruction with respect to scalar, and now the output of the network. So this is now the reconstruction using the spatially varying parameter that was produced by the network. And in some sense, so not in some sense, so what you have here, even though you use the CNN, but what you have here is a TV reconstruction. Okay, so it's highly interpretable. And this is, for instance, how the reconstruction will look like for a specific slice, and how the corresponding spatially varying parameter will look like for this slice. So you see it's really, really adapted to the data here. And some also quantitative plots. We also see that the output of the spatially varying parameter that corresponds to the spatially varying parameter is consistently better than the scalar one. We also did some dynamic denoising examples. So here I just want to point out the different. So again, we have some spatial temporal TV. So we have two parameters, the spatially varying. Again, the one that weights the spatial component and the one that weights the temporal component. And the interesting thing here is that when we have a moving camera, so when things are moving a lot, again, you don't want to regularize, to put a lot of weight in the time regularization. So this is what happens here. So the time component is very low. So you essentially regularize over space rather than time. But if you have a static camera, and that means that a lot of objects in your video sequence will remain where they are, then it makes sense to regularize, to put a lot of weight in the time regularization. So you regularize a long time. And this is why you see these large values on the parameter here. So what we saw before in the dynamic MRI, we also see it here in the dynamic denoising case for moving and static cameras. Just a few more things before we close. Of course, the question is, what T should you choose? So we said we unroll an algorithmic scheme. We unroll the primal dual method. Where should we stop? So where should we choose? What value should we choose for T? And we see here, for instance, that if we choose different values of T, we will produce different regularization parameters. So this is again for the dynamic MRI problem. That's why you see the spatial and temporal component. You kind of see like the same pattern. So where the heart is, you have like you have low values in the temporal component. So this is what we were saying before. But for instance, of course, the parameters look different. The difference here, one difference you can observe here is that for low T, so if you, let's say, stop your iteration at your primal dual iteration at eight iterations, then in general, you produce a highly regularization parameter that has high values. So it probably tries to compensate the fact that you have not really reached any sense of convergence in the primal dual. So it tries to compensate with some high regularization. But then the other question is like, let's say you choose some value T at training. At test time, so when you have some new data, do you want to use the same T, or do you want to use some higher value of T? Because you can see the scheme in two ways. The first is, okay, you fix your T and this is what you use. But because of the structure of the scheme, because it's like computation of lambda, and then you unroll the scheme, which is some algorithmic scheme with lambda fixed. Of course, you can send T to infinity as large as you want in order to have some convergence. And in general, for instance, if you train here, let's say if you train at 8, T equals 8, then it is advantageous at test time to increase a bit. So you get like a higher PSNR if you, for instance, if you run 32 iterations. But the interesting thing is that after a while it drops. So this is a characteristic of TV probably, or of the algorithm scheme. So along the some ballpark iterations, you don't get. It's not necessarily true that you will get the highest PSNR. It's not necessarily true that your solution of the variational problem will have the higher PSNR than all the iterates of the sample pop. So at some point it peaks, probably because the staircasing effect kicks in after one point. But what we also notice that if you test, let's say, with relatively high, if you train with relatively high T, then you're probably okay using that in the test time. So you will not have any. So this is, for instance, would be the black line here. So you would train with 256, and now if you test with more than 256, you don't get any advantage. Of course, okay, the method is that you want to train with sufficiently high number of iterations. So summarizing, so here we provided a simple, so it's like a concatenation of two networks, let's say, approach to select not spatially depending, not only spatially varying, but spatially temporally varying parameters for variation image reconstruction, so in particular also for dynamic problems. So we put all the black box nature of the power of the CNN to the parameter instead of the image itself. And there are some good arguments why you want to do that, because let's say the CNN, if you have your CNN producing your image, then you might have some artifacts there. But if you have the same artifacts on the parameter, then we have good indications that on your reconstructed image, these artifacts will not look that bad. So let's say if you have a completely noisy parameter, your image will not look noisy. So somehow any artifacts of the CNN will be suppressed on by the variational scheme itself. So of course it will be nice to get some theoretical underpinnings of this. So this I left it as an open questions. So we also presented some consistency analysis in terms of epsilon minimizers. It would be good to have that at least for stationary points. And another open problem, of course, I said we want to use some large T for training. And there could be ways to do that with computing some hypergradients or joint connections with these deep equilibrium models that people are using these days. So this is something that we left for future work. Okay, so that's all I want to say. Thank you very much.
Thank you, Kostas, for this very, very interesting, nice talk. So it's time for questions and comments. Please. David, please.
Yes, I have a few. Let
Yeah.
me just.
David.
Hey.
Yeah.
Kostas, thank you very much. It's really quite impressive work. And have a few questions. I will try to make it short so people can ask you more things. The first one is relating the networks just to generate these parameters. If you can go back to slide 16, I think. Just for a second, you have over there, you have two parameter to be estimated, right? You have the spatially, temporally, and the spatial and the temporary parameters, right?
Yes, it is two sets of parameters. So each one is spatially varying and temporally varying. So, but
and you have similar networks for both. You use like the same architecture for those two parameters estimation, or different architectures.
It was. I'm not sure how it was done in terms of the architecture. So you're probably talking about the output layer, how it was.
Yeah, I mean, because it's a unit, right? So
yeah,
I mean, I've seen it. I've been playing around with this deep image prior kind of thing.
No.
And it so happens that it is important architecture for the kind of parameters that you get. It basically, when you change architectures, it's somehow dependent.
Yeah, I mean, I agree that if you change the architecture, this is another future work that we were considering. If you use some kind of transformer, for instance, it would be different.
Correct.
Here, the important thing is that you wanted like a highly expressive network such that it's over parameterized, and if you get some new data, then it will really produce a regularization parameter which is really adapted to this data. So you don't have any, so you don't want to have any overfitting. And the way you do that is like this over parameterization. So now how this was, how was the output layer? I'm not so sure. We need to look at the paper, or I can.
I can
Andreas here,
but,
he could also tell you the details now a bit.
Yeah, sure, no worries. And I have another one, and it regards the activation functions that you mentioned that you needed to be continuous, and you needed to be smooth or just continuous. Continuous.
Just continuous.
So yeah, a real loose.
We didn't have any
right?
stationarity results, so just for minimizers.
Mm.
So just the necessary ingredients to get the gamma convergence in a sense.
Good. Okay, got it. And I have a final, like, I don't know if it's a question, more like a thought. I was recently reviewing some work on inexact bilevel bilevel learning and bilevel optimization in general. And you can see this kind of effect. I mean, in particular, the paper by Matthias and Landon, they have this this study on how they solving exactly the lower level problem, and they can solve it in exactly the upper level problem, which is kind of the same kind of strategy that's been done here, right? So you have like an unrolling scheme, the so-called, let's say, lower level for the primal dual problem, and then you have like a, I don't know, a stochastic gradient descent for the learning of the network or something like that, right? That also been solved inexactly. So they reported to have some kind of dependencies, not only on the amount of iterations that you use to approximate, but only on the type of algorithm that's been used. So it's supposed to change if you, for instance, you change a bulk for some other kind of algorithm. Probably you get different kind of results as well.
This is also something we discussed in the paper. So we had a lot of discussions.
Okay, I will definitely check that out.
It's a quite big paper, so we're a big team, so we had a lot of talks, a lot of numerics. This is another issue we considered. Indeed, especially for some applications, it might be beneficial to use a different algorithm also for implementation reasons. And of course, it would make sense to, because you want to keep your T as low as possible, it would make sense to have an algorithm.
Some acceleration.
Yeah, some acceleration thing. Yeah. Here the idea is to use the simplest thing. So TV regularization, of course, you can also think of other regularizers here. There's nothing that stops you. And the primal dual method. It's just this consistency analysis we did was very specific to primal dual, because we also wanted this bounce here.
Yeah, that's really
this ellipsis.
That's that's a quite impressive one. Yep. Thank you very much.
Yeah, welcome.
And great work.
Thank you.
Thank you. Just for there is a post in the chat, David, by Andreas Koffler, I think, explaining the construction of the unit. So probably you can check it also. Yes. Juan Carlos, please.
Okay, great.
Thank you, Kostas, for the nice talk. I just would like to continue on the argument of David, maybe. As a curiosity, if it is possible, do you think it's possible to incorporate some information of the bilevel problem within the unrolling scheme? So now you're using the Chambol POC, for instance, but maybe you can use the adjoint there or some information of the bilevel structure. Did you think about that maybe?
We briefly thought about it, but this is of course one of the things that we could do, we try to do, and also if you're interested, we can try to look at it. Yeah, this is the things we left for future work. It was simpler to produce all these numerics. Yeah, I don't know, implementation wise, what would be, because okay, if you want to use the joint equation, let's say you have to solve a linear system, so 2D plus time, I don't know how easy would that be in terms of implementation. So that was also one of the motivation we just did this simple unrolling here.
Okay, and you know the typical critique that it's concerning the spatially dependent weights is that it over regularizes and apply only for the training set that you learn from. Can you comment a little bit on that, on how general it is and so on?
Yeah, that was the point of using this CNN. So basically, okay, so is okay, so you do this training now, and because here you don't have only one parameter to estimate. So if you have only say one lambda, scalar lambda, and you solve that to you take the global minimizer, you have an overfitting. Also, if you have the spatially varying TV and you're minimizing with respect to the TV parameter without any parameterization of the network, then again you would have an overfitting. But now you are really over parameterizing these regularization parameters in a different way through this network. So let's say if you have the small lambda, just a scalar, then this will be over parameterized by, let's say, some thousands parameters of theta, and that will, and we also use this validation, so you never solve it to global optimality. You don't want to do that, but you use some validation. So you do some early stopping in the supervised learning using some validation set, and you base this early stopping at this point where this generalization to your validation set breaks down. So that's the point of using the CNN. It's highly expressive, so it's highly generalizable, and you avoid, in a sense, this overfitting that you would have with a simple bilevel.
Okay, because you have a lot of parameters, you can simply project.
Yeah.
Oh, okay.
I mean, of course, the images that you train are like of similar nature to the images that you test.
Okay, sure.
So you don't have like a fully generalization. Yeah.
Okay, thank you.
Thank you. So more questions or comments?
So David has also
David
discussion.
Yeah, David is now chatting with with Andreas. So
yeah, really
guys,
sorry about that. So I wish.
So anyways, I mean the contact of Kostas, I can send all the interested, if Kostas agree, all the contact information, so you can have a conversation.
Yeah, if you also want the slides, I can send them to you, and the papers in the archive. So
yeah, definitely. Yep, please.
On the first page.
Cool.
So the last two is the conference proceedings. We'll just like focus a little bit more on the MRI and the CT, but essentially, you know, everything can be also found in the first, the archive preprint.
Cool. Well, okay. Then you can chat each other if there is a collaborative outlook or something like that. Well, anyways, thank you, Kostas, for this very nice talk. Thank you all for being here, for connecting to this edition. For the next talks, we will change a little bit the organization. I will let you know. Anyways, I think we will have more or less one talk per month. So once we clarify this, I will let you all you know. Thank you guys, and well, take care.
Thank you for having me.
See you
see you soon, hopefully.
Thank you. Bye.
Great to
Thank
see
you,
you,
Kostas.
Kostas. Thank you.
Bye, guys.
Bye bye.
Bye. Thank you.
Bye, Andres.
Bye.